Thank you very much. Thank you, Tim, for that. So the title of this is It's Not Really About Air Change Rates. So I'm kind of poking the pig a little bit, I suppose you could call it. I'm just trying to stir things up a little bit. If you were here last year, I did a talk about Part 4, which had 14644 Part 4, which had not long been published. And I did a bit of talking, and we brushed on this kind of bit a little bit. So I'm kind of coming back to this in a bit more detail. In a bit more detail today, and it's to try and just make people think a little bit differently about air changes. Gordon did a talk this morning, and he mentioned that the 20 air change kind of myth, and that we should be thinking about things differently. And I'm kind of expanding on that and pressing that a bit further with my talk today. So just a little bit about me. I'm Managing Director at T-Squared Validair Limited. So I've been in the industry 35 years now, in the cleanroom industry. I am chair of LBI 30, which is the Cleanroom Technology Committee at BSI, and that's where we look and we provide experts that go on to working groups within ISO to look at updating of standards. I was fortunate enough to be on working group 3 when we did part 3, which was test methods. I worked on part 4, which is the design, construction, startup. I'm currently on the separative devices group, which is working group part 7. And there was a technical report on 14644 part 21 with particle counting techniques, and there's a talk tomorrow morning on that by a colleague in the industry. So Contamination Control Network, I'm the secretary of that, so one of the sort of founding committee members on that with a group of people, including Tim. And we do encourage people to sign up for Contamination Control Network. It's a free membership society, so please join that. I'm also a board member and examiner for CTC BSI, so Cleanroom Testing and Certification Board. I'm one of the examiners on that. As I say, and I'm currently the managing director at T-Squared Validair Limited. I'm not going to plug T-Squared at all. Because it's not a commercial presentation, so we can't do that, so, so I won't do that. But what I'm going to talk about, we'll talk initially about some assumptions about what these are for airflows. Some initial things to consider when you're looking at airflow for cleanroom design. I'll talk about ventilation effectiveness, which was mentioned earlier, recovery, cleanup and decay. We'll talk about source strengths. Then we'll look at air change rates, what suitable airflows we might need to achieve, and a little bit at the end about what next and what's missing and where do we go. So on the next bit, I think about some assumptions. So what we all kind of know is that really, so air change, if I've got a grade D room, I need 10 air changes. If I've got a grade C room, I need 20 air changes. Grade B room, I need 40 air changes and so on. We know that. That's what we need, don't we? That's right, isn't it? I just made all that up. It's not right. But there are assumptions that are made about air changes, and it's happened for decades. I remember when I first joined the industry, Annex 1 used to talk about 20 air changes. Used to talk about a value of 20 air changes. That's way back then. It doesn't now. But I had a little hunt about to see what documents have information. So Part 4, the previous Part 4, the 2005 version before it was updated, that used to talk about ISO 6 operational between 70 and 160 air changes. And his other numbers there. Quality assurance of aseptic preparation services talks about minimum 30 air changes for a grade B environment, 20 for grade C and D. ISPI guidelines has got 20 to 40 for grade C, grade D 6 to 20. And there's an IEST recommended practice, and that's got some very interesting ISO 720 to 200 air changes. So if you're selecting an air change rate requirement, you've got a pretty wide band to choose from there. Not really very helpful information. So if you wanted to be as a specifier, as a user, and I need to specify what my air change rate's going to be, where do you go? Where do you park yourself in that? As a designer, what do I do? Do I just turn up and go, ISO 7 operational? Well, we'll go with 30. Yeah? It's not very helpful. Not very helpful at all. So what I'm going to talk about now is the kind of initial considerations that we look at when we look into designing the clean room and looking at airflows for a clean room, what the kind of basic principles are, and where we take it from there. So go back to the very start of it. So we're looking at it's contamination control. That's our goal with airflow. It's contamination control. We're either protecting the product from contamination, we're protecting people from the product, we're protecting the environment from the product, whatever we're doing. It's contamination control. There's a basic principle. That's in ISO 14644 Part 4, and that's the kind of onion effect, where in the center you have your process core, you're protecting, and then you have your clean zone around it, your clean rooms around that, and you have different layers of protection. You feed in materials, you feed out finished product and waste, and people come in and out. And there's a basic principle of kind of zoning the areas that you're interested in. So that's kind of an early concept of what you do. After that, you're then going to be looking at how I've got options for how I'm going to segregate the critical area from a less critical area. In Part 4, there are 3 principles that you can use for doing that. So you've got a physical barrier, and it always says physical barrier with leakage, because even a solid wall leaks a tiny little bit. So it's a physical barrier with leakage, like an isolator as an example. Then you've got physical barrier with leakage and overflow. So that's your pressure cascade, typical room-to-room flow under a door. And then you've got aerodynamic. So that's without a physical barrier. That's where you're using airflow on its own to create a barrier and to give you that contamination control and that protection. So there's the segregation concepts you choose to use when you're looking for, or a combination of those throughout a facility. Then it's about what airflow concept you want. And in principle, there are 2 options. So you go for unidirectional airflow, or you go for non-unidirectional airflow. So you're either going to have air moving in a turbulent motion throughout your room, or you're going to have air in a unidirectional. If it's unidirectional, it's like a piston effect. So velocity is what's important there. You're displacing contamination. You're pushing contamination away. You're creating that barrier with unidirectional airflow. Alternatively, it's non-unidirectional, and that's a dilution effect. The contamination is in the room. You're diluting the concentration of contamination with nice, clean air. And so most of this talk I'm going to do is going to be about the dilution effect, about how we look at clean rooms. This is where our air changes come from. And I try and convince users who are putting specifications together to not put an air change rate requirement. Don't say we need a minimum of X air changes, because you don't know that that's what you need, and you're also potentially guiding a designer to give him a get-out-of-jail-free card where he goes, well, you said you wanted 20, that's what we gave you. So I try and convince people not to put those kind of requirements in, and I'll talk about a bit more why. But I'll move on now. Ventilation effectiveness. So this was mentioned earlier. Gordon talked about it in his talk this morning. So ventilation effectiveness is about how evenly the clean air works its way around the suite. So what even distribution you get. So a ventilation effectiveness index, a value of 1 will mean it's that perfect mixing. You've got perfect mixing of air that comes in and mixes perfectly with the suite before it leaves the suite. In reality, in real life, we don't really ever get that. That's not very easily achievable. So you have an index, and there are a couple of ways in which that can be measured. So there's a thing called a CRE index, So the concentration of airborne contamination at the exhaust divided by the average airborne concentration of contaminants in the room. That's one way of measuring ventilation effectiveness. It has its shortfalls depending on where contamination is generated and where you're measuring, etc. A better option, and the one that I'll talk about, is an ACE index, which is the air change effectiveness. And that's saying basically that the effectiveness of the ventilation in a suite, if I'm here, so the local air change rate here, divided by the air change rate of the whole room, will give us a ventilation effectiveness value. If it's perfect mixing, then the cleanup that I get here, the air change rate I get here, will be the same as I've got for the whole room, and we'll have a value of 1. But in reality, we don't get that. We get areas that clean up quicker than others, and so we don't end up with that kind of ventilation effectiveness value. But you can do that with at multiple positions within a room. So it's a local air change rate divided by the overall average clean room air change rate. Gives you a ventilation effectiveness. The reason for the ventilation effectiveness I'll talk about in a few slides, and that'll explain how that fits in as a value. Obviously, when you're looking at designing a room from new, you don't know a local air change rate versus an overall air change rate, so you're going to make an assumption on the ventilation effectiveness value that you're going to apply. So to give you an idea of so there's it's quite an old drawing, but there's a pretty crude way with a pretty poor ventilation effectiveness. So we've got short circuiting, whatever you want to call it, going there. The air's coming in at high level and going out at high level. It's not really reaching down where the operator is or critical location, so you're going to have a fairly uneven airflow. You've got short-circuiting. It's a pretty poor setup, that one, for that approach. I hear sometimes as well people go, well, I've got a grade D room, so because it's grade D, I just do high in, high out. It's okay, but you've still got short-circuiting potentially. You're still not particularly efficient. Your ventilation effectiveness isn't very good. So I don't really understand the concept. Go high in, go low out. It doesn't really matter what grade it is. It's less critical. What you tend to find is the grade D areas, you have to pump a load more air into it to push it down to get to the areas at low level. Otherwise, you still get a contamination problem at low level. Here's a couple of other examples. So here's one where the air, on the left-hand side, the air blows directly downwards. So it's just like a perforated diffuser. The air is blowing straight out of a grill and directly downwards. The one on the right-hand side has got a diffuser, and it's moving air in different directions, and in both cases, we've got low-level extract. So generally speaking, what you'll get here with the one on the left-hand side is you're going to have a different level of ventilation effectiveness in different parts of the room quite considerably. Where the critical surface is, in that centre point, you've got a very high air change rate effectively at that local point because all the air is going down there first before it's spreading and mixing in the room. So you'll have a high value there and a much lower value in other parts of the room. When you look at the one on the right-hand side, at the kind of, let's say, 1 metre where particle classification is typically carried out, you're going to have a fairly even ventilation effectiveness. You'll have a fairly good, in that kind of setup, the air is kind of diffusing around the room and blowing around. So the one on the right is probably your best option. But if you're designing, not always your best option, because you might want to think about, there might be a reason you want that critical surface to get additional air, in which case you think you design slightly differently. Actually, I do want to be putting air directly down here because I've got something I need to protect here and I want to direct the air towards it. But generally speaking, that's going to give you a variation of ventilation effectiveness across a room. The other one is going to give you a more even ventilation effectiveness. The other thing to consider about is extract grills, where you put your extract grills. So you have them at low level, but you might want them at low level near where activity is higher than have them at low level on the other side of the room. So you have a situation where a high activity, which is generally contamination generating, is happening over one side of the room, and all that contamination has to go all the way across the room before it leaves. So the location of grills is also important. I've got a picture of some different types of grills here. So you've got swell diffusers. The second one in is a perforated plate, but it's a box perforated plate. So it actually comes down from the ceiling as a perforated plate and the air diffuses out. Third one is a traditional perforated plate, air goes straight down. The fourth one is a four-way throw diffuser. I'm not going to talk about it now, but there was an article written, Nigel Lenigan did a study on different types of grills in clean rooms, and he wrote a paper on it. It's in CACR magazine. It's quite old, 2014, I think it was. But it's worth a read. It's interesting to see that they put particle counts throughout a room. They did airflow studies. They put different grills on at different flow rates, different air change rates for the room to see which one worked most effective. And they did find that they felt that the perforated plate, the box perforated plate, worked extremely well, as did the four-way throw diffusers. So onto clean-up and recovery. So this is all leading us into how we get to what we're talking about. So ventilation effectiveness, if we park that in our minds for a moment, we look at clean-up. So what happens with regard to a clean room? There's a test in part 3 where you can demonstrate how quickly a room cleans up, a decay rate for a room. In part 3, you generate particles effectively and you watch a decay of particles and you record it. And what you're looking for is a section on a straight line. This is a plot, so we see at the beginning, particles are released in the room, particle concentration gets really high, it's mixing with the room, and then it starts to decay as the clean air is diluting that contamination and contaminating away. And it's the exponential decay on that graph is a section on there that you're interested in. The curve goes straight in the centre, and that's the bit that is your decay. That's your decay time or decay rate there. And then when it starts to level out again, you're getting to the natural kind of level within the room with a natural background. So that's recovery cleanup. You can do that test. If I show this in a different way, so recovery cleanup. Here's an example of a recovery cleanup based on air changes, where on the left-hand side we've got the particle concentration as a percentage of the initial concentration. So if you're looking for a clean-up from 10% of the original concentration, we can see the time that takes. And I've plotted, there's 3 graphs plotted on there. One's 80 air changes, which is, the colours aren't so great. 80 air changes is this one here. And you've got 40 and 20 air changes. And that shows you how and that's it's in perfect mixing. So that's an example of a recovery rate in perfect mixing. So from that, you'll see 99% of particles, so like 100 times cleanup, 100 times cleanup particles, 20 air changes will be 14 to 15 minutes. 40 air changes will take 7 to 8 minutes, and then 80 air changes in 3 to 4 minutes. You can see the kind of difference that it makes. If we then, when I spoke earlier about ventilation effectiveness, you need to, if you're doing an original design, you need to determine a value for ventilation effectiveness because it has an influence on how quickly that happens. Because the point I'm getting to is that the air change rate is the recovery rate. And that's the time the air change rate influences the recovery rate. It doesn't necessarily, on its own, influence a result of how clean the room is going to be, but it will be what the recovery rate is. With the ventilation effectiveness, there was papers were done a while ago, and a typical value for a ventilation effectiveness was set at 0.7. There was a study done of about 25 rooms, and kind of the average of those rooms was about 0.7, and it was a value that's not a bad starting point if you want. Use a value of 0.7. So if we apply that, if we use an ACE index of 0.7, so actually what we'll find is a 15-minute cleanup takes 18.4 air changes, but actually when you add the ventilation effectiveness, it's about 26 air changes. So if we're looking at a grade B room from completion of operations, that clean-up period in Annex 1, where it talks about going effectively from operational to at rest, that is 100 times clean-up, that's at 0.5 micron. We're going to need probably 26 air changes for that to happen, for that clean-up to happen, to meet that requirement. But 26 air changes might not give you a room that's within class. That might not be enough air. It might be way too much air. And on one below there is a 15-minute clean-up grade C for 10 times is 9.2, but it's 13 if we add an ACE index into it. So the point, okay, so the relationship, so the decay rate, recovery rate, is the same as the air change rate. There are, at the end of this slide, there are some reference to some articles. Bill White wrote a paper on it that explains the equations that match, that give us that thing that we know that actually, when you measure recovery rate, you're measuring an air change rate at a local location. So it's the same thing. So when we go back to the ACE index, if you remember, we were talking about ventilation effectiveness and the ACE index. So the local air change rate is the same as the overall air change rate, which actually means the local recovery rate is the same as an overall recovery rate. So you can also say a local recovery rate divided by an overall average air change rate is applicable. So you can use recovery rates to calculate what your ACE index will be. But in the absence of being able to do that, then 0.7 is not a bad value to have. So that's the relationship there that we get with ACE index. So source strengths. So we've gone to source strengths now. So what we're saying I'm saying air change rates tells us how quickly the room will recover. It doesn't, on its own, give us an understanding of how clean a room will be, how diluted it will be. So because we have source strength. So the contamination we're worried about is what's generated inside the clean room now. We've got a nice clean room we want. So we've got people in the clean room, they'll generate contamination. We've got machinery in the clean room that will generate contamination. And we may bring contamination in or out. And so the source strength is basically the number of particles per second that something's going to generate. And if you've got a person just standing there, they're walking about, they're naturally generating particles. And they'll just keep generating particles and generating particles. And some will fall to the floor, the heavy ones, some will stay airborne for a while. But you'll generally just get dirtier and dirtier in the room. So we need to deal with that by dilution. And so we need to get a suitable airflow for that to happen. So I've got some air volume flow rate calculations now, which come out of, it's using a very simple formula that's in part 4 of 14644. And it's that. So the supply air volume flow rate that you need in a clean room is based on the source strength divided by the particle concentration limit that you're looking for that clean room. And there's an epsilon factor in there, which is the ventilation effectiveness. So how good your, if it's a 1, that's a true perfect mixing clean room. the ventilation effectiveness is 1, but we know we don't get that, and I mentioned earlier, 0.7 is not a bad value to throw in. You might want to throw in 0.5. 0.7 is a value. But that will give you the air supply flow rate that you need to maintain a concentration limit in that room with an assumed ventilation effectiveness. There's a few more bits you can add to that. So if there's unidirectional airflow cabinets in the room that are also cleaning it up, you can take those values away. You can get rid of particle deposition, so particles that are falling to the floor that aren't airborne. You can use a calculation to get rid of those. We're going to stick with the easy bit in white for the purpose of this explanation. But that's in part 4. It's a way of identifying the air volume flow rate that you need. It's not based on an air change rate. It's based on source strengths within the room. So, of course, the challenge is what are the source strengths in my room, and we'll come on to that as well. But that's the theory that we would work to. If you've got an existing facility, you can use the data. You know what you can calculate what your ventilation effectiveness is. You even know what particles your people are generating. You can actually use it to tune down your clean room potentially by using data like this. So when we're looking at suitable airflow, so that's the airflow that we need to maintain class, right? But we're right on the limit there. We've used a maximum concentration limit. We're going to be running that room at its concentration limit like that. So what other things do we need to think about for suitable airflow? So someone's designing a suite. There are a number of things that you need to think about with regard to the supply airflow. So you need fresh air. Every person needs to breathe fresh air. We need oxygen. So you need to have a value for oxygen that you need to do. There'll be heat gains in the room. Designers will need to compensate for heat gain. There might be extraction in the room. So you might have a local exhaust system, or you might have an isolator that's extracting to atmosphere. You've got to make that air up. So you'll need that. You need to know what that value is. You'll probably want to pressurize the room, generally speaking. So you'll have some leakage from pressurization. You'll need to compensate for that. Then you might have a recovery rate requirement, a cleanup, a decay rate requirement that we were talking about earlier. You might have that Annex 1 requirement for within 20 minutes and ceasing operations. So you might have that to think about. So you've got to, how much air do I need for that to happen? That's my air change rate do I need for that to happen? And then you have your contamination, the source strengths we spoke on the previous page. How do we deal with those? So if we go on to and exclude the slight crudity of these graphs. So we've got 4 people in a clean room as an example, and they're generating a load of contamination. Okay? So let's have a look at it. The size of this room, we've got a 5 by 5 by 3 metre room, so 75 cubic metre clean room. We've done some assessments, we've done some clever design, and we know that we want these are just numbers. I was just use an example. We need some fresh air. We're going to need 0.032 metres cubed a second. We're going to need 0.2 metres cubed a second to be able to deal with heat gains. There's no extraction from the room. We don't need to compensate for that. We've got some pressure in the room. We want some volume to deal with pressure. And we've got some values there. And then we also we've got 100 times recovery. Yeah. So we've got an ISO 7 operational clean room, so like a grade B clean room. And we want to do a recovery of, say, in 15 minutes. So this was when it used to say 15 to 20 minutes in Annex 1 before it changed to 20. It was based on 15. And from this kind of setup, from that room, to get my cleanup rate that I need 0.541 metres cubed a second, which gives me 26 air changes per hour. And that will give me my recovery. So all of a sudden, air changes are important now because I need it for recovery. I need 26 air changes for recovery. So if we carry on looking at this one, we've got this room, this contaminated room. We've got some air supply we can go on now. So we know we need 0.451 for recovery. So now we look at source strength. So source strengths I've got down as 17,000 particles per second per person in that room at 0.5 of a micron. That's what I'm basing this on. That data is from a study that Bill White did a while ago, and that data is available. And I've just picked that as an example of some data. So we've got that. Our concentration limit is 352,000, and I've gone, oh, well, let's make sure we're about half that, so I'll put 176,000 as a value in. Go back to that equation, the Q and source strength divided up. Go to that equation. We do some maths, and we end up with an air change rate. We end up with a volume of 0.552. So that's what we need to have us at 50% of concentration limit during operational activities. And that's an air change rate of 26.4. Coincidence that it's close to 26. There's no true correlation with that. That's just a coincidence in the numbers that I did. And then I want to, the next slide is just going to explain. So the air supply comes on. We've got showing a nice little blue air supply coming on. And therefore the contamination starts to drop down. We're still generating contamination, but we're diluting it now with a sufficient amount to maintain the cleanliness. So next thing, I'm designing this particular clean room, and I've kind of estimated these kind of values I need. But then the design of the clean room changes. I no longer need the big bit of process kit I had in there. My process kit can be smaller, so I can make my room smaller. Which hopefully this will do. Yep. So I bring the ceiling down. I only now need a shorter ceiling. I don't need the ceiling to be so high. So what that influences, did that button not work? No. There we go, so we've got the air supply coming on. Yeah. So that changes the height of the room. So it was 3 metres, now it's 2.4, so the volume of my room changes. So to achieve my 26 air changes per hour for recovery, my air volume changes. I don't need 541 now, I need 433. So someone says, well, we can make your room a bit smaller, we don't need as much air to go in there. That's true for air changes. But my contamination is exactly the same. My contamination is not reduced. I've still got as many particles per second being generated. So therefore, when you look at that equation, my air change rate, I need the same 0.552, so my air change rate requirement's gone up to 33.1. So if you're designing based on air changes, you're missing a key thing here. You're not looking at what you need to be looking at because it's influenced by the size of the room. And yet the concentration level is influenced by the air volume flow rate and the number of particles that we're all generating. So the key I want to take away from this bit, I understand, is that what we'll find is that an air change rate is relevant for recovery and cleanup. You need to, there's an excellent correlation between those two. But it's actually a function of air flow rate and room volume. So the air change rate is actually effectively an output from your design. It's not an input into your design. Aside from any recovery rate requirement, it's not an input into your design, it's an output. You get your air change rate when you've determined how much airflow rate you need. And that air change rate is based on room volume. So, next point here. So, what's missing in all of this? We've had this conversation about this. This thing seems great, excellent. We can work how much we know what people shed, etc., etc. But do we really know what people shed? There has been some studies done. There is probably a need for more studies to be done. We need more data. And I said this last year, at the end of my talk last year. I said the same thing. So we need more data. So we can do some estimations and we can use some historical paper information, but you're still going to have to put some buffers in as designers for confidence. But we do need more data. There's two articles there which give quite a lot of information on source strengths for people and some equipment in both of those papers there. I've listed here some other papers that deal with and articles that talk about air volume flow rates, that talk about air change rates, recovery rates, and there's a number of papers that you can grab onto for doing that there. So I've gone through that a little bit quicker than I thought I would, to be fair. But I think the key thing I'm trying to point out here is that so often I get involved in a project at early doors and you've got users who are saying, we need to specify what our air change rate needs to be. And I'm saying, don't specify what your air change rates to be. Leave that for the designers to tell you what your air change rate's going to be. That's their job. That's not your job. You tell them that you need a room to be this grade with this many people in it. Tell them what gowns you're wearing. Tell them what the quality of those gowns are. How many people will be in the area. How often they'll be in the area. If you've got a recovery rate requirement, what that is. And give that to the designers and let the designers then take that responsibility of coming up with what their airflow rate needs to be and what your air change rate needs to be. And I've finished a little bit quicker than I thought, but
Okay.
Thank you.
Thank you, Steve. So we've got time for lots of questions for Steve. So, Morgan.
Do you find in non-unidirectional flow clean rooms, the style of diffuser makes a difference in terms of recovery rate?
Yeah, massive difference. Yeah, huge difference. Yeah,
I do as well.
Yeah.
In the US, people are still stuck on using dump diffusers or swirl diffusers or quad diffusers, and it really makes a difference from particle state control, recovery rates, and also smoke studies. At least my experience.
Well, you in your talk you were talking about airflow moving upwards, and you get swirl diffusers classically draw air up into them. Even when you look at things like dump flow, when it blows the air straight down, it hits the floor. Where's it going to go after that? It's going to head up again.
A big issue with isolator designs or rams, because when they open the doors, that bounce effect can cause the air to travel into the open door.
I was on a project a few years ago, and the clean room had been designed quite well in the sense that the location of the grills, it was four-way flow diffusers. We had extract grills at low level all around, and the isolators were put in, and the intake for the isolators was at high level. And immediately the four-way flow diffusers that were blowing air straight into the top of the isolator, and we weren't getting very much coming at low level. And it was just a poor, that poor interface between, there's an isolator here, so we're putting this bit of kit and it's going to draw air from the room. Where's it drawing its air from? Because that has an impact. And that's all part about when you look at layout, about where you want. So no, that needs to be intaken at low level. But answering your question, definitely dump flow, you get a very, very quick recovery rate underneath it and a poor one in the corner.
That's why it's really important to pick your sample location.
Yes, yeah. See, recovery rates, historically, we'd stick it in the middle of the room, we do a recovery rate, and we go, oh, we got 9 minutes, brilliant, and everyone's happy. But actually, you use it to do more than one location. Think about what might be considered the worst location in the room. Do a recovery rate and where you anticipate the worst location to be. And it gives you more useful information. Or a recovery rate where the highest activity is going to be. And then that will give you information about what the recovery rate's like, where you think the contamination is going to be worse, because it's generated worse there.
A question just while I've got the microphone, because I might forget it if I don't ask it now. Steve, have you got any experience, or does anybody in the room have any practical experience now where this is a more engineered and scientific approach to constructing a room around air volume supply rates, but there's a bravery involved here when you start to consider the particle concentration limits that you're prepared to accept, the source strengths of the personnel or the processes that you're going to run, and we're designing to perhaps a more critical limit within the room, which is energy conscious, energy efficient. Does anybody, or do you have any experience of what the regulators, inspectors, or sponsors of the companies that are taking this type of approach feel about it?
I have no concept of what the regulators would say, but then I suspect the regulators won't care in a way, because unless they're really hung up on an air change rate, and other than that, if you approve the room, you qualify the room and it's working correctly, then you've done it. The risk, I think, is with the designers, most definitely. I mean, that's their challenge, because they're going to want to put a buffer of comfort into all of that. And Gordon was talking this morning about tuning things down so they fall over and fail. How close to that fall over and fail do you want to get? And it's interesting on this. There's a talk tomorrow. One of the young professionals, I don't know where Derek is in the room. Yeah, he's going to do a talk tomorrow. He's come all the way from Netherlands tomorrow to do a talk which is on this subject and about using source strengths in the design of a clean room. So that'll be an interesting talk tomorrow. And we've also got Keith Beattie doing an update on the dynamic control, which again is looking at sources of source strengths and adjusting airflow to compensate for it. But it's you're right. It's a challenge. I mean, an approach that you can make is you've got designers with really good experience and really good user experience. Use that experience to start, and then challenge it with some source strength information. So kind of, okay, well I've done this. That's where I think we are. Okay, let me look at it from a different perspective, and to do the source strength. So I throw that into the equation. Go, am I super over engineered this, or have I under engineered it based on that, and gain some knowledge from that experience? Because one of the challenges that I think you have with designers of designing clean rooms is that they tend to disappear once the at-rest bit's done. So designers will design it and they go at-rest, and then they disappear. And then the users are struggling with contamination wherever they've got, and the contractor's gone, I've built a great room. It was ISO 5 as built, because it's easy to get ISO 5 as built. and yeah, without really seeing what's happened afterwards.
No, fair enough, thanks Steve. I'll come over in a moment, Gordon, I have seen you.
I was just going to ask how you would advise people then to devise their user requirement specifications, because it seems to be an art. You specify that you want, say, an ISO 7 room to house 1 or 2 isolators with a specific capacity, and do you just then leave it to the designer? Because it's, how do we then know that this specification has been met other than via the non-viable particulates? How do we know that the airflow is appropriate to protect the hatches opening until it's been built and until you've done the smoke vis studies? And even then you see the air travelling up and you think, well, this is air from the floor going right past my entry into the isolator. I don't want to accept this. But then we're told, oh, but it's diluted, it's fine.
So if I turn that question on its head slightly with you and say, let's say you'd said we want 20 air changes. And so they design it, with your designer meets your user requirements and designs it for 20 air changes, and you see exactly that same problem. Yeah. Where do you stand? Effectively, the designer's going to say, we've met what you asked for.
Yeah, I'm not speaking about the air change rates, just about generally sort of clean room design. If you try to specify in your user requirements specification, you want a new clean room that has a 2 isolators, say, meets ISO 7, but you want protection of the hatches because you're doing manual disinfection into your isolators. So I think from what you were saying is that we need to leave it to the designers, but sometimes, I don't know, sometimes you think, well, do I really want your sort of diffusion if I'm not getting first pass there, past my critical zones, which would be the entry into my isolator, or do I include that in my design specification, user requirement specification?
Your user requirements, but I mean, this whole topic, user requirement specifications, is all on its own. So I think, generally speaking, in user requirements, try not to put too much stuff that's design-based. Let the designers do the design element. But put the key, your user, what you want it to achieve. If you've got specific requirements you want it to achieve, that's what you tell the designers to do. The designers will do their work. You then do a design review, and hopefully you can challenge that at that point. CFD is another option. Morgan mentioned that earlier, a really good tool. So where you can, you're mimicking effectively what the airflows are anticipated to be, and that gives you that area of confidence.
I think sometimes it's useful to have the discussion with the designers, but I think I've worked for the NHS, and it's having the expertise within the NHS to be able to challenge what the designers are suggesting, and then understanding the rationale and being able to critically appraise the information thereafter. So we like to stick to, well, this is what I did 20 years ago. So.
And and that's and I see that a lot. So I see that a lot of that cut and paste from history.
And we've also had, I've worked in a facility with a clean room with the inlet and the extract both in the ceiling. They had massive airflow. We had massive air change rates they could barely get in, but just so that we could
Get cleanliness,
get it clean.
Changing thoughts. I've given the microphone to Gordon. We're not going to turn this into a committee meeting.
Very quickly, I was just going to do my little demonstration about the importance of air supply, air distribution. So if you hold a piece of paper up and blow at it, it bends. If you now suck with exactly the same air volume, it doesn't move. In a non-unidirectional airflow clean room, it's the supply air and how it's distributed that delivers your ventilation effectiveness and your mixing. The return air locations should be evenly distributed, but they're not as mission critical. So the supply air dictates the ventilation effectiveness, and it's important to get that right.
Thank you, Gordon. Very good demonstration there. Paul, I saw you had your hand up. Is there one last question?
I was going to say just what Steve said about CFD. That's probably part of the URS stage when you go to your designers. Because if you know a rough layout of your isolators in your room, CFD can be quite useful just to do that confirmation aspect. It's interesting from the NHS because I work with the NHS on Section 10 units which aren't under the MHRA, and the QAPs that you mentioned and the HTMs, which are the Health Technical Memorandum, say it's got to be 20. But the clean rooms are quite small. Traditionally they're quite small. You know, the roofs are really about 7.5 foot, just above me. So actually, you could be needing 30 because you might have 3 isolators and 6 people working in that room. But the specification on HTM is 20, but it might actually need to be 30. Sorry?
So it's a minimum of 20.
Minimum of 20, yeah.
But I mean, that's the, when they, and that's again, it's because there's no specific knowledge available to the NHS.
And you still tend to see that in user requirement specs. Yeah, it is. Yeah.
But you make a good point about small rooms. If you look at changing rooms, are small, and so they go, oh, well, 20 air changes. Let's say 20 air changes in a changing room, and it's a tiny little room. There's not hardly any air going in it, and yet you've got somebody that's gowning and creating a lot of contamination, and yet you've chosen to dribble air into that room to meet 20 air change requirement. Yes, yeah, exactly. And you have loads of problems in your change room, and you're dragging contamination through from the change room into the main room. And yeah, and your clean room guy's gone.
So changes upon us. ISO 14644 was changed in 2022. Yep. So a fairly recent publication. This conversation continues. This is change, and as Steve's presented from last year and from this, it's not just about air change rates. So the mood is changing. And that will create a lot of discussion, both individually and across industry.
Is there the capacity now? I know there was years ago, but is it becoming more commonplace now to be able to model airflows for a given presentation?
CF, computational fluid dynamics. Yeah, it's. I think that the software has got better.
We charge a lot for it.
Yeah.
Yes.
But it's probably money well spent. I mean, Morgan, you'd agree with that for sure.
Yeah.
So,
You'll save yourself a lot of time and energy to do CFD. It's worth the money. Putting in a new line, how many $1 million are you going to spend on it?
Yeah, it's just that it's rarely budgeted for.
But-
We've got one facility, they both their isolators for a new refurbished facility. They've been in storage since September last year. They haven't got a URS for the clean room yet.
but
All right.
so just one thing on that. With CFD, the date you get out is only as good as the date you put in.
Yeah. All right, I'm going to stop us there. Good conversation. I'm sure there's many more questions that could come out on that as well. Steve's going to be around through tomorrow. Steve's chairing tomorrow, so he's going to be here a lot. If there are any more conversations about that, please continue them. We're going to invite now the last presenter up. So Steve, thanks again.
All right, thank you.
Thank you.